So now we're going to take a look at the natural logarithm, but we're going to start with something we know from before. So what we just discussed in the last module was y equal e to the x, and the derivative dy dx equals e to the x. We were using function notation before, so we'd have f at x equals e to the x, then f prime at x equals e to the x. This is the same thing using Leibniz notation. But now I want you to think back to grade 11 and grade 12 advanced functions, that exponential and logs are inverses of each other. So y equals e to the x is the inverse of y equals log ex. So I'm going to start with the exponential function, y equals e to the x. If I'm looking for the derivative of log base e, that means I'm doing the inverse of this. Inverse, if you think back to grade 11, means switch x and y. So I get x equals e to the y. Now I'm going to work on the derivative of this. Well, the derivative of x is just 1. The derivative of e to anything is e to that exponent. But here's where I have to be careful. Now my function that's in the exponent is y. Well, the derivative of y is dy dx. So I have to multiply that here. If this was just an x, the derivative is really dx dx. So that's how we get it to be 1. But in this case, because that derivative is y, I can't just multiply by 1. 1 is the derivative of x. The derivative of y is defined as dy dx. But now I can solve this for dy dx. And I get dy dx is equal to 1 over e to the y. But if you go back up to this line, ey and x are exactly the same. They're equivalent. So another way to write this is 1 over x. And because when I did this and inversed it, I did log base e, which we call ln. So ln is just notation for log base e. Just like mathematicians said, if there's no base, we understand the base to be 10. If it's ln, we understand the base to be e. So the derivative of ln is 1 over x. Because I did the inverse, therefore this is just another way of working with ln. So in general, if f at x equals ln of x, then f prime at x is 1 over x. And we can do some examples, and now chain rule is going to come into play as well, because if f at x equals the ln of g at x, then f prime at x equals 1 over g at x multiplied by g prime at x, and you'll often see this just as g prime over g. So if you have a function here that you're taking the ln of, it's not just x, then it's 1 over what you're taking the ln of, multiplied by the derivative of that function, and you can just end up moving it to top, because 1 times g prime is g prime, g times 1 is g. So we can do some examples now. So y equals the ln of 5x. So dy dx equals. So because this is a ln, I do 1 over what I'm taking the ln of. So it's going to be 1 over 5x. But now I have to look inside and I have to multiply by the derivative of this, which is 5. The derivative of 5x is 5. And in this case, I can divide top and bottom by 5, and my answer simplifies to 1 over x. A lot of the times it will, but be careful, it doesn't always work that way. Because let's look at example 2. Y equals ln of x all over x cubed. This is a quotient, so we have to go back to our quotient rule. So dy dx is the derivative of the top times the bottom. So the top is ln x. The derivative of ln x is 1 over x times the bottom minus the top times the derivative of the bottom all over the bottom squared. Here's where you have to be careful though. I can't multiply this x and this 3x squared. This is similar to when we were doing our trig work, that x is part of the ln. It's locked with it. This 3x squared isn't, so I can't put them together. But I can clean this up a little bit. X cubed divided by x is x squared. I'm going to bring the 3x squared in front, so I definitely keep it away from the ln x. X cubed squared is x to the 6. Now on top, I can factor out an x squared. So I get x squared, 1 minus 3 ln x, all over x to the 6. So all I did there was common factor out an x squared. And now because I have x squared on top and x6 on the bottom, I can divide. Dividing, you subtract exponents. So my final answer is 1 minus 3 ln x over x to the 4. F at x equal the ln of x squared plus e to the x. So f prime at x is going to be 1 over what you're taking the ln of. So the x squared plus e to the x goes to the bottom. You can keep it in brackets or not, it's up to you. But now I have to multiply by the derivative inside. So the derivative of x squared is 2x plus the derivative of e to the x is e to the x. I can't common factor anything out of the top, nor can I common factor anything out of the bottom. I can't start canceling because these are pieces. I can only cancel after I've written it as a product or everything is separated. We'll do one more example with the equation of a tangent. So find the equation of the tangent to y equal ln of x squared over 3x at x equals 1. Equation of a tangent is modified slope. So I have y minus y1 over x minus x1 equals m. My x is 1, so that's going to be x minus 1. I'm going to figure out my y. So at x equal to 1, y equals ln of 1 squared over 3 times 1, which is going to just give me the ln of 1 over 3. And now I want to talk about this a little bit, because remember, a log asks you for an exponent. So if I ask you for log of 100, it's asking what exponent on 10 would give me 100. So that answer would be 2. So when I have ln of 1, ln means base e. It's asking what exponent on base e would give me a value of 1. Well, the only way you can get 1 out of an exponent is if you do e to the 0, so the exponent is 0. So this literally becomes 0 over 3, which I can reduce to 0 over 1. So I am going to have, whoops, that's not my slope, that's my y value. So it's going to be y minus 0. I was thinking that was my derivative for a second. So that just equals 0. So ln of 1 is 0, because it's asking what exponent on e do you need to make 0. Now I'm going to find my derivative. So y equals ln of x squared over 3x. So dy dx. I'm going to combine my knowledge of natural logarithms and quotient rule to do the derivative of the top. Well, because the top is a ln, I'm going to have over x squared, and then on top I'm going to multiply by the derivative of what I'm taking the ln of. So in this case I'm taking the ln of x squared, so my derivative is 2x. So that's just the derivative of the top at that point, times the bottom minus the top times the derivative of the bottom. So the top is ln x squared, the derivative of the bottom is 3, all over the bottom squared. I'm going to do some work to clean this up. 2x times 3x is 6x squared. I have x squared on the bottom. That's going to be convenient because those will go away. Minus 3 ln of x squared. I brought the 3 out in front, so I didn't want to put it with that. All over 9x squared. 3 squared is 9. X squared is x squared. So I'm going to end up with 6 minus 3 ln x squared over 9x squared. Now, if I was doing some more work with this, I probably would common factor out a 3, but now I'm just going to put x equal to 1 in here to get my answer. So at x equal to 1, I'm going to end up with 6 minus 3 times the ln of 1 squared all over 9 times 1 squared. So that's going to give me 6 minus 3 times 0 all over 9. Because remember, ln of 1 means what exponent on e does it take to get 1. Any base exponent 0 is 1, so that's going to be 0. So 6 over 9, which reduces to 2/3. I'm going to come back to my modified slope formula and put 2/3 in for my slope. So I have y minus 0 over x minus 1 equals 2 over 3. I apologize that that's a little messy. I'm going to cross multiply to get 3y equals 2x minus 2. 3 times y, I don't need to do 3 times 0. 2 times x, 2 times negative 1. I'm going to write it in standard form. My x is already positive on the right-hand side, so I'm going to leave it there. And I'm going to bring the 3y over and put it in order. But there is the equation of our tangent.